When you talk to an AI today, it really feels like human creativity, or doesn't it? It feels like logic, reasoning, and language, but if you peel back that slick interface and look deep inside the machine, there's no magic. Underneath it all, AI is really just billions of numbers being multiplied and added together simultaneously.
And that brings us to a pretty fascinating paradox. Why does this revolutionary technology, something poised to change literally every industry on Earth, rely so heavily on a chip originally built just to render video games? As AI integrates into everything we do, the hidden hardware beneath it is quietly becoming the world's most critical infrastructure. Let's explore exactly why in this explainer.
Section 1. The hardware behind the AI. Let's strip away the illusion of the chatbot and look at the actual physical systems doing the heavy lifting. You see, AI isn't just some software program magically floating in the cloud. It's a massive, synchronized physical system working inside colossal data centers. We're talking central processing units, graphics processing units, extremely fast, high-bandwidth memory, thousands of miles of networking cables, and massive liquid cooling systems just to keep the whole thing from melting down. This entire stack has to work together perfectly.
Moving on to part 2, the math of intelligence. To really understand why this specific hardware stack is necessary, we've got to look at the underlying math of machine learning.
When an AI processes your prompt, it's passing data through a neural network. At a fundamental level, the math running those networks is called linear algebra, relying heavily on an operation called matrix multiplication. Just picture a giant spreadsheet of numbers that all need to be multiplied and added. But here's the kicker. These calculations don't actually have to be done one after the other. They can be split up into thousands of smaller, totally independent calculations.
And that's exactly why repetitive work can be parallelized. Because this mathematical workload is so incredibly repetitive, it demands a very specific type of processor. Not one that's just super fast at doing one thing at a time, but a chip literally built for massive, parallel, simultaneous execution. Which brings us to Section 3, CPU versus GPU explained.
The central processing unit, or CPU, is the core computational brain of any server. It's totally optimized for flexibility, complex branching logic, and completing serial instructions very quickly. On the flip side, the graphics processing unit, or GPU, is designed for a completely different kind of workload. Instead of a few very powerful cores, the GPU has thousands of simpler ones. It's optimized for massive throughput, meaning it can take a huge volume of the exact same instruction and push it all through at the exact same time.
Think of the CPU as the head chef in a high-end restaurant. The head chef makes complex, critical decisions, manages the entire kitchen, and handles highly unique requests. But if you suddenly need to flip 10,000 burgers at the exact same time, the head chef is actually the wrong person for the job. For that, you want a factory line, a GPU, where thousands of identical steps are executed simultaneously. AI training at its core is essentially flipping millions of mathematical burgers.
Now, this raises a pretty obvious question. If GPUs are so incredibly powerful at doing this math, are CPUs becoming obsolete? Do we even need them at all in the age of AI?
The answer is a resounding yes. We absolutely still need them. Recent research analyzing multi-GPU setups notes that performance frequently drops, not because the GPUs are maxed out, but because the CPUs actually fail to keep those GPUs busy. The CPU acts as the project manager. It runs the operating system, coordinates the network, and feeds all that massive data right into the GPUs. If your project manager is too slow, the entire factory line grinds to a halt.
Let's move to part 4. The bottlenecks of AI. We've talked a lot about the immense power of this hardware, but now we need to confront the physical and economic constraints threatening this entire revolution. Because a blazing fast GPU factory is completely useless if the supply trucks are too slow to deliver the materials. We face a few really critical bottlenecks today. Memory bandwidth limits and data movement constraints are massive hurdles, because it takes significant time and energy just to move data from memory into the processor. And then there's the sheer physical footprint of these data centers. We're talking massive energy consumption and extreme cooling requirements.
To put that energy consumption into perspective, consider this jaw-dropping number from the Stanford AI Index, 25,300,000 watts. That's the estimated power draw required just to train the Llama 3 language model.
And when you look at that historically, it's pretty staggering. Back in 2017, training the original transformer model took about 4,500 watts. Fast forward to 2024, and Llama 3.1, required over 25 million. That is an exponential and, frankly, dangerous scaling of power requirements. We are literally building systems that demand the energy footprint of entire small cities.
But there is an impressive counter-narrative here. Hardware engineers are fighting back hard with efficiency. When you measure computational efficiency in floating point operations per second per watt, the modern B100 architecture is nearly 34 times more energy efficient than the NVIDIA P100 from 2016. So we're actually squeezing vastly more mathematical operations out of every single watt of electricity. Yet raw silicon alone doesn't solve the whole problem. Ultimately, software is what makes the hardware usable. The only way we achieve these incredible speeds and efficiencies is through highly optimized software ecosystems, like NVIDIA's CUDA platform, or specialized inference engines built in languages like Rust. Without that complex software layer managing the memory and batching the calculations, all that expensive hardware would just sit completely idle.
Section 5. Beyond the GPU. Because as these workloads diversify, we're entering an era that looks beyond just throwing more GPUs at the problem.
There's definitely a growing nuance to this hardware battle. Recent research proves that for smaller, on-device tasks, like running an AI directly on your smartphone, highly optimized CPUs can actually outperform GPUs. When you factor in the time it takes to transfer memory back and forth to a mobile GPU, a multi-threaded CPU can sometimes generate text faster. So the future isn't just a binary battle. It's really about picking the right tool for the job.
We're also seeing the rapid rise of custom silicon. Take the Tensor Processing Unit, or TPU, built by Google. This is an application-specific chip designed purely for the massive matrix computations of neural networks. It strips away all the graphics rendering baggage of a traditional GPU to focus entirely on AI workloads. It just goes to show that the hardware landscape is diversifying very quickly.
So, to summarize the trajectory we're on, we are moving from just seeking raw speed to maximizing efficiency. We're shifting towards specialized accelerators like TPUs, while simultaneously optimizing CPUs for local edge computing. But most importantly, we are increasingly treating the entire data center, the networking, the memory, the cooling, and the chips, as one giant, unified, holistic computer.
Which leaves us with this final, somewhat philosophical thought. When you sit down and converse with a large language model today, it feels profoundly smart. But as we've seen in this explainer, underneath that slick interface is really just a factory line of processors mechanically churning through billions of matrix multiplications. It forces us to ask, is this system truly intelligent? Or have we simply discovered that human-like language is just a problem of massive, parallel math? Thanks for joining me on this deep dive. Keep wondering and keep learning.